Hello, everyone. Welcome to the UFS webinar series. This webinar is hosted by NWS Office of Science and Technology. The goal of this webinar series is to enhance communication and share the advancements in all aspects of the UFS in both research and operational settings. My name is Bhavana, and I work with Yang Trey, who's the program manager at OSTI, to coordinate and deliver this webinar. Feel free to contact us if you have any comments and suggestions. Today's webinar is going to be presented by Georg, who's the Chief of Earth Prediction and Advancement Division at GSL. Speaker Georg will be introduced by Jian Wen. We have a couple of housekeeping items that I would like to bring to your attention. I lost my screen. The microphone and webcam have been disabled. You can use the webinar dashboard to raise the hand if you would like to be unmuted. The presentations should last about 45 minutes, followed by a Q&A session for the last 15 minutes of the webinar. Please type in your questions in the question box during the presentation. The presenter can view your questions and answer them during the Q&A session. With that, I would like to pass over the presentation to Jian Wen to introduce the speaker. Jian Wen, you're muted. You have self-muted, Jian. That's why I think I can't unmute you from here.
Oh, good. Thank you.
There you go.
Thanks. Greetings, everyone. My name is Jian Wen Bao. It is my great pleasure and honor to introduce the speaker of today's UFS webinar, Dr. Georg Grell, who will talk to us about the challenges for improving subgrid convective cloud representation in the UFS. This is a subject in which we should all be deeply interested because it is concerned with how the UFS RTO physics development project moves forward to meet the UFS community's expectations. Georg is a fellow of the American Meteorological Society and currently leads the Earth Prediction Advancement Division at GSL. Georg is well known as a principal architect and developer for a few mass flux convective parameterization schemes that bear his name and the widely used MM5 and WRF-10. He was a recipient of the Hawkins-Smith Prize and an NOAA Outstanding Scientific Publication Award. Ladies and gentlemen, please join me in welcoming Georg.
Georg, one quick thing. You have to share your screen. I have stopped sharing mine. Yes, we can see it.
You can see it?
Yes.
All right. Let me just. Is that the right view?
Yes.
Okay. All right. I'm honored to have the opportunity to talk to you all about convective parameterizations. I will try to give a bit of an overview first of some of the challenges for parameterizations in general. But what I cannot do in this talk is to talk about all challenges and how developers are trying to handle them. That would be just simply way too much. And I hope that will become clear by the end of the talk. I would like to give special acknowledgements for development and providing slides to Grell-Freitas from NASA and Hannah Barnes, who is a young scientist here at GSL. So I will first give you some basics on convective parameterization. I will talk a little bit about the background on grayscale issues and why there is a problem. I'll give you some examples of early and current ideas on what to do on grayscales. I talk a lot about other issues too, and those will be mostly focused then by using the Grell-Freitas convection scheme. So what do we do when we parameterize? Well, we know of a process that is important for model simulation, but it cannot be resolved explicitly. And then that means we need to express that effect in terms of processes that are resolved in the model, in terms of other variables. And what is usually necessary to do that? Well, of course, you need to have a physical understanding of the process. Otherwise, you can't really do much with it at all. And scale separation. And this term has become important because of the ever increasing resolution that operational centers are going with right now. So if you see this beautiful picture, would you think we have a good understanding of the processes that we have to parameterize here? One can see a lot of very small scale detail from clouds at different scales. Shallow convection, there seems to be some organization along lines. I don't know whether you see my mouth here, probably not. There seem to be clusters, and the whole thing looks like a cauliflower. You see a lot of details popping up. It seems like you would need very high resolution to actually really come up with a realistic picture of this. So convection and clouds are very complex, multi-scale processes, and are also very beautiful, of course, not only to a meteorologist, but especially to a meteorologist or a weather geek like me. So people are smart. They will make assumptions, post a hypothesis, test things for case studies. Folks have worked on convective parameterization for a long time, since it is of great importance if you want to improve your skill scores. Convection kind of drives much of the circulations in the atmosphere because it's so widespread in the tropics. So many folks have come up with many different approaches, and that's kind of what this slide brings out a little bit. First, you need to decide on where the convection will be and how strong it will be. That's usually termed closure assumptions and also trigger functions. And there's many examples of that out there. Stability closures, the well-known famous quasi-equilibrium closure. There's moisture convergence closures. There's non-resolve forcing, vertical velocity, and then of course the regular trigger functions. And then what you need to do is you need to determine how the convective clouds will modify the environment. So you need to know, what does a cloud look like? Is it a plume? Is it a bubble? Where does the air inside the cloud come from? How important is entrainment, detrainment, lateral mixing? What physical processes are important in the cloud? The microphysics, condensation, evaporation, interaction with aerosols. How important are downdrafts? Convection usually comes with downdrafts. How does the surrounding air respond? If you have mass flux going up, something else is going to happen outside. Something is going to go down. And what does a mass flux really look like? And then number 3 would be, can scale separation be guaranteed? If you're trying to simulate the impacts of convection within the grid box, the statistical effects, you really need to be able to separate the scales. It means you don't want the model to be able to simulate the process actually explicitly. And for some modeling applications, there's atmospheric composition interactions, aerosol and microphysics, aqueous phase chemistry, scavenging from tracers. And I'm not going to talk at all about number 4 here. So scale separation is one of the main topics in this talk. And I'm showing this picture to indicate how obvious the problem is. So if you have one grid box, may this be the one grid box. Forget about that little airplane thing coming out there. You could see a lot of clouds in there, and it might be fairly easy to come up with the statistical effects of all the clouds in the grid box. Actually, it's not easy. There's other problems, but you don't have the scale problem. That might still be okay if you double the resolution. But at some point, resolution gets so high that some of these clouds, you can see that up in the upper right corner, almost occupy the whole grid box. Now that's still not enough to actually resolve that cloud, nowhere near enough, but you also get into trouble with trying to parameterize it because there's really no scale separation. And that also means that the forcing and triggering may have to be different on those type of scales. So if you look at this picture, do you think there's agreement on how to parameterize these beautiful designs from Mother Nature? There's deep clouds, middle clouds, and low clouds. And I've shown you the one slide with all the different ways of doing this. Of course, there is absolutely not agreement on how to do this. To summarize the background info, challenges in convective parameterizations are enormous. The proper treatment of convection in the tropics is extremely important for longer range global forecast skill, longer time range, that is, medium range or S2S. Scientists have worked on these challenges for over 50 years. Currently, more challenges are being added almost by the day rather than resolved. That doesn't mean people don't try to resolve the other ones too, but there is more coming just because we know more about convection, we know more about physical processes, so that means there's going to have to be parameterizations within the parameterizations. Finer and finer resolutions in NWP models make scale awareness, or the grayscale issues, as they're also sometimes called, a fairly new but very important challenge. So grayscales are defined as resolutions where there is a mix between being able to resolve convection and having to parameterize it. This is usually also called the convection allowing model simulations, resolutions. This is an example of some diamond runs. To start learning more about the behavior on these scales, the Diamond project was started over in Europe, where modelers would run these models for a 40-day run on convection allowing resolutions, and then compare model runs with analysis, observations, and other models. Shown here are simulations done by NASA, with a snapshot picture on August 3rd, not too far into the simulation, obviously because it's compared to observations, and on different resolutions. And what you can see is you really have to go to about 6-kilometer horizontal resolutions before the mesoscale convective systems, at least, seem to be represented reasonably well. And that is, of course, just looking at the picture of precipitation or brightness, temperature, not necessarily on when you compare to results with respect to skill scores. It's a totally different story. So grayscales really seem to be here to stay, because a lot of people want this realistic looking representation of mesoscale convective systems and convection in general. So let's look at that grayscale issue in more detail. As I mentioned, there are a bunch of different approaches out there, but here I'm focusing on a widely used mass flux type approach, which uses this simplified conceptual idea. If you derive the vertical eddy fluxes in a more mathematical way, this conceptual picture does fit, but it is not the only idea that fits. But anyway, a lot of parameterization use this approach, envisioning the cloud as a plume. So I will concentrate on this. So usually you have all of this maybe in a 50-kilometer grid box, and you're at least fine with the scale separation. If you're talking much higher resolution, then what you can see is that, like the mass detrainment up on clouds and also down at the downdraft bottom, as well as possible cumulus-induced subsidence, may not be at all in the grid box. And as a matter of fact, the cloud may just be right on the border of the grid box, and maybe even lateral entrainment and detrainment would have to be split. So obvious problems, again, the mass determinant at the top of the cloud and the surface and the compensating subsidence are the most likely to be outside the grid box. And that is will be outside the grid box when delta x is less than 10 kilometers. And the finer the resolution, the worse the assumption that every feedback is within the same grid box becomes. What may happen physically in those model simulations? Well, subsidence may have a strong heating and drying effect, and that keeps the explicit scheme from becoming active, and that also keeps the three-dimensional numerical model from taking over, from actually being able to start resolving some of it. It makes organization of convection almost impossible. It also has a very strong diffusive effect. The flow will become too viscous for the model to simulate the dynamics of explicit convection that may be resolvable. And that viscous effect has also been found by other scientists in PBL and large eddy simulation applications. We're talking here about convection, but the same ideas really also exist in boundary layer parameterizations, except on a much higher, finer resolution. Another problem, probably caused by oversimplified conceptual picture, is that parameterized convection may be stuck over areas of forcing, such as mountains, and may not move with the flow as dynamically simulated convection would. It's because convection really doesn't have an idea of this. The parameterized convection, that is. It moves with the forcing. So there's very little chance to catch organization of cloud clusters. Common problems if no convective parameterization is used on those grayscales. That's actually something that is used. Then convection usually takes too long to develop, and once it develops, it's too strong. You end up over forecasting the high thresholds. For operational forecasting, it depends on the application. For medium range or S2S applications, results are quite often worse if no convective parameterization is used. For storm scale severe weather forecasting, not using a convective parameterization may be preferred. And again, this of course also depends on the other sets of physics parameterizations that are used in the model. So operational centers are more and more applying grayscale resolutions in their models. That means they have to use one of these approaches. And number one, as I mentioned, convective parameterizations are being used without any modifications on grayscales because of better results. Who cares where the subsidence sits as long as we conserve mass and it rains and the skill scores in the end look okay? Parameterizations are inherently inaccurate anyway, which they are. Or no convective parameterization is being used because of better results too. That argument usually comes along the line, doesn't look right to use them. Parameterizations are inherently inaccurate anyway. Or number three, scale-aware convective parameterizations because of better results. Could be maybe an ensemble average of 1 and 2, but that's only a fun thing that I put in here. There's more and more now that will go to either way 2 or 3 instead of 1, but not all. And that might come clear in the next slides that I'm going to show you the two different approaches. So this, for example, this is again provided by Grell-Freitas as a publication out at GRL, Geophysical Research Letters, that compares 3 simulations. Those are the 40-day simulations. The green framed one is a scale-aware GF scheme. The red one is using no convective parameterization, and the blue one using is GF without any scale awareness. So compared to number 1 on the slide before. And on the left side, you see the precipitation from GPCP and also GPM. If you look at GPM, that's a 0.1 degree resolution. So that's more like what we are after anyway with a higher and higher resolution. Then you can see that you would probably think the green or the red corresponds better to this, the way it looks like. It's just physically more realistically looking, while the blue one looks much more smooth. If you look at 40-day averages, on the other hand, if you look at the top, for example, again, the blue is the GF without scaling, then it has the least error and the least bias for winds, moisture. It also has the least bias for temperature, least RMS error for temperature. It does have a slightly higher bias for temperature. But in general, if you use GF in this case, without any scaling, you get the best results. And the same as you can also see below in looking at the average zonal U wind speeds, where actually it's pretty clear that the runs without any convective parameterization, the red, is the worst representation of the whole simulation. And then we're going to the other side, to storm scale, folks. This is an example from the HRRR, the high resolution rapid refresh, which usually runs without a convective parameterization, and for a reason. You can see the top here is observations, and in the lower left, you see the HRRR forecast using no convective parameterization. And just is only focusing on an issue that you sometimes see with the HRRR in weakly forced environments. And that comes again, it's in line with what I talked about before. Because the explicit scheme can't really get active quickly enough to produce the storms that are observed. On the other hand, if you use a scale-aware GF scheme in this case, then you get these fairly large areas with light precip. And this depends on that threshold value that's in GF. The higher that threshold value is, the lighter this precip will be, but it turns off other stuff too. Now, what that will do to the scores is it will actually improve them. You can see the blue curve here, both in the CSI score is better, and in the bias is definitely better too. And you can tune that more, and you can almost come up with a bias of 1. But it'll look really bad if you want to see any storm scale features, which is what, of course, the sphere storm guys are after. So some historic attempts to address these problems with various modifications in parameterizations, focused on scale awareness now. A very interesting one was from the UK Met Office in the 80s. If you look again at that picture, at that conceptual picture, what they do, they decided to let the parameterization only do transport of mass. So forget about the compensating substance, but let the model do the compensating substance. It's a very appealing idea. You can only do it with a non-hydrostatic model, but it's very difficult to find any publication on this from UK Met Office side. If you're trying to talk to them, they actually, it seems like they almost don't want to talk about it. And then there's Kuhl and Butt. That's published in Quarterly Journal. It's very similar to one, and they claim some success. And this is at least used in an experimental version operational model that is used by the German Weather Service, but it's not in operations to my knowledge. And I don't know whether it has gone anywhere since then. And then there's another very promising approach, a superparameterization approach. That's in the works since 20 years already. And it still can't be used, probably because it's too expensive. And the original versions till fairly recently were also not scale aware. That's different now. So there's still work that's being done on this approach. It is promising, but so far it hasn't gone anywhere into operations. Luc Gerard in France tried to develop prognostic equations for fractional error coverage and the vertical velocity inside the cloud to come up with a better treatment of the vertical eddy fluxes. And then there's the approach that we originally did to call the G3 scheme, where we applied the parameterization over a range of grid points. That's done in a version of the Grell schemes, one of the various different versions. And then it's Arakawa approach, which relaxes the sigma requirement by defining a relaxed adjustment. And that is now used in some way or the other in many different approaches. It is simply a scaling. I'll talk about that a little bit more. 1 and 2, in contrast to 6, may not be consistent with the derived eddy flux equations, but are purely based on the conceptual ideas from figure 1. 5 appears to work for constant grid spacing, the G3 scheme, but requires communication across grid points and cannot easily and smoothly transition for irregular grids. So there's two disadvantages in this. 6 offers a smooth transition, but is it really the way to go? Okay, Arakawa's approach. What they do is they rederive the vertical eddy transport equations, but assume that in the grid box, it has to converge to a cloud resolving simulation. When they do that, they can show that there's a simple dependency here where the term on the very right side here is the original conventional convective parameterization for full adjustment. And by using the fractional area coverage by the active cloud draft, they can then derive a vertical eddy transport that corresponds to the solution as it converges to a cloud resolving model simulation. Now, while this mathematically is a really nice approach, you can see that if you look at this little thing here and you display it here, this is not really physically very realistic. And I'll get more into this. So more on Arakawa's approach. Many attempts exist to put some sort of physics in the scaling factor, not necessarily only the fractional coverage, and I'll show you that too, but problems do remain. ECMWF, for example, uses the convective adjustment time scale to bring in some scale separation. They're doing an interesting approach because they have the German Weather Service empirically determine the scaling factor dependence on cloud resolving simulations and find that the mass flux maximizes at 8 kilometer delta X. And then they adjust the equation so that it converges to 0 as the resolution increases. Similar approach by the Tietke scheme from WRF, as implemented by Wei Wang, is just a different scaling. And what quite a few people will do, they add some additional conditions to it to make it not quite as rough on the physics. The scalar Kane-Fritsch scheme is also using a similar approach. More historic attempt on 6, scaling the tendencies with GF. We try to determine the fractional area coverage, and the only thing that worked for us with good results was to use a simple entrainment relationship to calculate that sigma term. And then where lambda here is the initial entrainment rate assumed to characterize a PDF for the mass flux distribution of deep convection, the vertical mass flux distribution. And that all depends on a certain threshold. It cannot go past the threshold, meaning you can't cover more than, say, 70% of the area. And the larger that threshold, the faster conversion goes to 0. And to avoid a too quick turnoff, what we do is we change the initial entrainment rate when the threshold is hit. This leads to a decrease in cloud size. As can be seen here, that's an example of idealized three-dimensional tropical cyclone simulations. The top heating profile from the convective parameterization, 27, 9, and 3 kilometers. You could see how that decreases drastically. And then the lower end to show the cloud top stuff is actually the same thing with 9 kilometer, 3 kilometer, and 1 kilometer delta X. You can see the 9 kilometer is way out of range. These are small tendencies, but for 3 kilometer resolution, the cloud top is now at 7 kilometer. Using 1 kilometer resolution, cloud top is at 3 kilometer. So the clouds become more shallow. Of course, that is not really solving this problem. As we know now, I've shown this picture before. I'm not going to spend more time on this. So what to do for applications that reach the cloud resolving scales? What are we supposed to do? Well, in my opinion, to understand physical processes with a very strong relation to convection, we should stay away from convective parameterization completely and adjust resolution so the simulated process is fully resolved. For operational applications, it is usually not feasible to do that. So then what do we do there? The scaling is somewhat unphysical. Convection is not restricted to just one grid box. And that is an assumption in all scaling approaches known to me, except maybe that G3 approach. So an answer may be to consider impacts on neighboring grid points. That would be possibly a mixture between scaling and the 3D applications. There could be dependence on the type of forcing too. Use that type of approach only when there's light forcing, which is when that problem is usually the worst. Stochastic approaches might help some. Could probably be used pretty effectively, actually. However, the physically most realistic approach would be to mix between 3D application and scaling. And this is really important in the tropics, and that's why it's becoming more, or will become more of an issue in the future too, in my opinion, if we want to make significant progress in advancing the skill scores. Okay, some aspects that we're trying to address in the Grell-Freitas scheme, and I'm not going to give you much detail on this scheme, only a few things. JF is scale aware. It was the first approach to successfully apply the Arakawa approach without looking at details, of course. This is a picture from an MPAS simulation, which is the hardest on the scale awareness because it's a very smooth transition of 50-kilometer resolution in the outside grid. And then you could see these red lines as the resolutions increase to 3 kilometer in the inside. And it shows you the total precip in the top panel, the convective precip in the lower panel. You can see there's a smooth transition in the convective precip from mostly convective in the tropics to barely any convection in the inner grid. While that's the opposite for the total precip, indicating that the model has been taken over, which is what we want to do. And the original paper also describes, the 2014 paper from GF also describes a 3D approach from the predecessor, the G3 scheme. And a unique feature in GF is a different approach to updraft and downdraft mass flux. Many parameterization developers spend much energy on assumptions and hypotheses for determination of entrainment and detrainment rates, which are key for the vertical mass flux distributions. We went the other way, and there's other ways out there too. Ours is not the only other way. We assume that deep convection can be characterized by a certain cloud type with certain vertical mass flux distribution, and that is characterized by a PDF that supposedly describes the vertical mass flux distribution. And then after that, entrainment and detrainment follow from the mass flux profile. And the level of maximum mass flux, which is important to determine the PDF, is determined by stability profile. We use 3 PDFs, one for deep, one for congestors, and one for shallow convection. How does it look? Here's a comparison, a single column model application, TWIs, comparing to observations on the right side, wind profiler data in black, seapole data in red, and the dashed lines show deep convection, the dotted line congestors convection compared to the model on the left. And as you can see, the deep mass flux corresponds pretty well with the observed. A lot of the currently used parameterizations have that maximum actually significantly lower than what's observed. And this is also the case for the congestors type, although for the congestors type, it is much more difficult to determine the maximum of the PDF. And ours is probably too low a little bit, as you can see here. For the shallow convection, we assume that the PDF maximizes at or just above the cloud base, which is quite often in agreement with large eddy simulations or observations. This one shows a comparison on the left side to large eddy simulations from BOMAX from Pierre Sievesma. So we're happy with the deep and the shallow convection. We may have some more work to do with the congestors. More developments in the GF parameterizations. I'm not going to focus on what's in black here, cloud body retracement. Memory is used to influence PDFs, cloud body retracement. Below cloud body space evaporation. Subsidence terms, everything flux with positive definite choice. But we're focusing on the green ones because that's issues that are currently being discussed in the community out there in Europe as well as in the US. Consistency between the microphysics in convection and resolved microphysics. Things like cloud movement, downdraft cold pool advection and organization, and also aerosol interactions. So that's like the last part of my talk here, where I'm going to talk a little bit about these things. And a lot of these experiments have been done by Hannah Barnes, who's working in GSL in our lab, in my division actually. And she's coming from Bob House's group, so fortunately she also has some knowledge about what the observations look like. And storm motion in convective parameterizations, as I mentioned before, quite often you see that convective precip is stuck over mountains, it doesn't move away. That's because the forcing doesn't move and convection doesn't know that it should move with the airflow. This is not a completely new idea what we're trying to do here. Frank and Cohen in the 80s already envisioned the downdraft could be used with a time lag to kick up new convection. In the GD scheme then in 2002, we added flow direction to this, but advection is a better way to go. It's much smoother. And so we're moving the convection and then using the downdraft mass flux to create new convection and change and modify the environmental properties in the direction of the movement. Here's an example. That's WRF results. We have a little bit of an issue trying to get this to go in FE3 because it's not easy to implement two-dimensional advection of a scalar in the UFS using average U and V fields from certain levels, but it is work in progress. Anyway, what you see in WRF here, one run with storm movement, that's the black lines for precip, one without advection, that's a green line for precip. And the storms are expected to move to the east. We see a little bit faster movement with the advection included, but much more distinguished is the surface pressure difference and the 2 meter theta differences, which are much more pronounced when you include this effect. So we have really hope that this will be an interesting new addition to the convective parameterization. And another thing that is now already active in the UFS too is the application of number concentrations in GF and bringing microphysics a bit closer in agreement. And this is Grell-Freitas was actually considering implementing a much more complex part of the Thomson microphysics in GF, but that would be very expensive. And I'm not even sure where he is with that project. I think he's online, but Hannah's approach in collaborating with Greg Thompson is very inexpensive, and that can be used with any parameterization. So that is the one that is currently in UFS. The cloud water approximation is based on cloud water mixing ratio from GF, water-friendly aerosol characteristics. Cloud ice approximation is based on cloud ice mixing ratio from GF and the ice-ice temperature relationship. And you can see differences in the WRF runs. This is, for example, a comparison field experiment November 2011. And for the polar orbiting environmental satellite from PSL. And that for this case, actually, the modified scheme agrees better with satellite observations. Now, currently receiving much attention at operational centers are aerosols. And there was a working group for numerical experimentation, a WIGNI group that was established to look at aerosol impacts on numerical weather prediction. specifically interaction with radiation. Most people had that impact in there, and some folks had interaction with clouds or the indirect effect. And in the end, of course, the impact on data assimilation is also interesting here. Especially if you go to more and more sophisticated physics that use double moment microphysics, they need some sort of information about droplet number, aerosols, whatever. And radiation needs it already, and what we currently use is climatology. You would think you can do better than climatology when strong sources of sinks exist. Very good example is currently the HER smoke, which actually is much closer to predict the surface temperatures right. Even it's still too warm, but it's about 10 to 15 degrees cooler in the smoke areas than the operational model. And currently there's a phase 2 in progress, which is looking at the impacts of aerosols in more detail, as well as the impact on subseasonal to seasonal predictions. What we do in GF is we have 3 changes. We change the constant auto conversion rate to an aerosol dependent Berry conversion. We change the evaporation of raindrops. That's based on a paper by Jiang and Feingold, based on an empirical relationship where the precipitation efficiency is related to it. And that was not enough. After talking to Graham Feingold on the hall here at SREL, he was laughing at us because of those assumptions and said, you need scavenging. So Hannah Barnes implemented a way of adding scavenging through memory impacts. So this is what you get for a 1D test with the GF convective parameterization. Again, there's no scavenging here, can't be, because there's only one time step. There is no single collier model here. What you can see in the lower right, the rainwater is moved up in the cloud. You get much more cloud water ice detrainment in the upper levels, which causes cooling and moistening. But you can also see cooling in the low levels from stronger downdrafts. That's from the second change because of the precipitation efficiency dependence. That, of course, depends on the environmental conditions. If it's already at the upper limit, you can't really evaporate more. You can't make the downdrafts any stronger. Again, we expect the biggest impacts of this impact is, again, probably going to be in the tropics. So in a 3D test, and this will be showing some results from WRF Chem too. We've been looking, this is for the phase 1 of this WGNI test and the Brazil case, because that should be able to give us ideas on both radiative and microphysics impacts. So we were running several WRF Chem domains, and I'm only going to show results from 1, 2, and 3. That goes down to cloud resolving or cloud convection allowing grids. What's important here is to note that the model was run with gas phase chemistry, modal aerosols, aqueous phase chemistry, and double moment microphysics. This is a very expensive setup. It's not easily possible to run this on operations. It still has less variables in the current CMAQ model, but it has almost as many. So it's a very expensive run. So this is what you get for averaging 20 runs each for 72-hour forecasts for the total burden PM 2.5. And the convection permitting simulations are over northeast Brazil and over Colombia in this area where there's actually low AOD. You'll see in a minute why that is. It goes a little bit into areas with higher AOD too. You can see the fires showing up, of course. It was a fairly active fire season in Brazil. Okay, so systematic and random shortwave differences from these runs. Averaged over 20 runs, 3-day forecasts. What you can see is first there's random changes that are just simply caused by different location of clouds. And they're not interesting at this point. Then there's random changes that look like random, but they're not quite random. If you would average it, you actually see a slight cooling. You can see that fairly clearly down in southern Brazil here, which is a bit more organized convection in that area. And both of these areas did have higher aerosol concentrations. And then you can see areas with systematic changes that showed up in almost every one of these 20 runs. The one on the left, for example, this is shortwave radiation differences, is of course in the afternoon. You can see that in the fields. And you can see this area of much more shortwave coming down over the cold water here in the Pacific regions. And that is something that was also seen by PNNL, Jerome Fast group, up at UW and PNNL, not UW, and compared well with observations there too. And then you could see the cooling over central and northeast Brazil, which is simply the radiative effect. And this red area there, which is actually a warming or a more shortwave radiation reaching the ground. So what do you do when you use, what happens if you use a convective parameterization? Well, if you don't turn on the aerosol awareness, you see the direct effect only. That's kind of expected because you get less shortwave radiation reaching the ground because of the interaction with radiation. And then I show results here with convective parameterization, the aerosol awareness turned on, and you can actually see some red spots there up in the northeast in Colombia, Venezuela, in the very northern part of Brazil. And we haven't quite figured out yet why that is. We need to rerun this case anyway. It's probably a little bit over predicting this impact because at this point we didn't have the scavenging impact in there yet. But interestingly, it agrees with the convection permitting simulations with full chemistry and physics. So we figured that was kind of a nice success. So in summary, convective parameterizations have been causing headaches for more than 50 years, and they might just continue to do so for a long time to come, certainly past my retirement, and I'm not afraid to say probably after my death still. Much interesting work is going on in the world. Could be really interesting too for young scientists. There's some very large funded projects in Europe. UK Met as one example to improve various aspects of convective parameterization. So this could be at least a great opportunity for young scientists to get in the game and maybe sell their soul to convective parameterizations. And I'm just listing a few here. This is my last slide. Scale awareness with an exclamation mark. Forcing what controls strength and location of convection. Discussion on this is ongoing and will continue to be ongoing. As I said, there's many different ways in there. There's also some parameterizations like the GD scheme, like the GF scheme too. We allow several closures, including W closures, moisture conversions. How much sophistication is used in has to be necessary in parameterized clouds? Microphysics consistency, is it important? Aerosol interaction processes. How about memory? What contributes to organization of these things? What processes need to be realistically represented for the feedback? Updrafts, downdrafts, probably yes. Radiation coupling, very important and very tricky. Cloud water ice detrainment interaction with microphysics. You detrain cloud water, microphysics will pick that up and get you cooling right away. Interaction with other physics parameterizations in general. Should convection be represented with a single plume, an ensemble of plumes, PDF resembling plumes, bubbles? I just had some talk with Junichi Yano over in Europe, and again, there's a lot of interesting approaches out there. How can we implement memory impacts in organization? Scavenging of aerosols, downdraft cold pool movement was mentioned too. Where is stochastics most important and where is it necessary? Because there is a lot of stochasticism in convective parameterization. I'm just mentioning forcing the PDF representing plumes, microphysical processes. You can think about more things there. And then finally, but not least, can we use machine learning in a physical meaningful way? We were already thinking about using it to maybe at least show why our PDF approach works for representing plumes. And with that, might be able to try to answer some questions.
So George, there are a couple of questions that have come up. I don't know if you can view them or if you would like me to read them out.
Probably better to, if you can do both, that would be the best. But
if you click on the questions ribbon in the dashboard, you should be able to see them.
The what ribbon?
Questions. There's a ribbon called questions in the dashboard.
In the chat?
Yeah, not in the chat. There's another one called questions.
Oh.
Maybe it's best, Bhavana, you just read out the question.
Okay. So this one is from Ben Woods. He says, some recent research has shown that aerosols did not inhibit convection in tropical cyclones. In light of this, should the approach with aerosols be modified?
If you're talking about the approach that we're using, we're not there yet to answer that question. Because it can go either way. I mean, we've seen cases, we've run this with WRF over the US, where convection actually was increased in intensity. So we've never tried this in tropical cyclones yet. And we're not absolutely, we haven't put it out there in the public yet either. It is in the scheme, it's not turned on, and it will not be turned on until we're confident that it produces reasonable results. Hannah is currently looking into this with the UFS.
Okay.
Does that answer the question? I hope so.
The next question is by Cliff Math. He says, is there another approach? Only a small portion of the planet has convection. Might we simply run 1 to 2 kilometers for those areas with coarser resolution elsewhere? Simply, sorry, I lost the window. Simply have the determined regions where convection might potentially develop.
Yeah, and that's kind of the super parameterization approach is kind of a little bit like that. And of course, if you have a grid like MPAS or there's some other irregular grids out there, you might be able to do some of that too. Although with MPAS, it might be difficult to create one of those on the fly. But yeah, I mean, that would be good. It'll still then get you into trouble with shallow and congestive type convection, but at least you can take care of the deep convection, which is probably the most important to begin with. So yeah.
Next question is by Krishna Kumar. He asks, are you thinking that the ML AI based models should be trained on high resolution model with fully resolved moist convection for operational applications?
Yes, that's pretty much the line I was thinking about. I think machine learning will be a great tool in the future, and I certainly think we're nowhere near the end yet of using true high resolution cloud resolving models to understand what's going on and being able to move some of that to operations by simplifying it a lot. But that's also why we're doing the WRF Chem simulations for very complex setups to make sure we have at least some base that we can trust a little bit to. Doesn't mean we can fully trust it yet. Everybody knows that the aerosol dependence is, it's highly, it's a research thing. But anyway, it's great to be able to use LES models or cloud resolving models. LES models is probably the best approach, but so yes.
That looks like that's the last question. We don't have any more.
Okay.
Havana, could I ask you one question?
Go ahead.
George, thanks for the informative and comprehensive presentations. Given what you reviewed about the current challenges, what do you think that in short term, how can we address those challenges in our UFS R2 project?
Well, in our UFS R2O project, it's the interaction with microphysics that is really important, right? And that is a very sensitive parameter because, like, I mean, you know that if you get cloud water, I mean, we've seen that in tests too. You detrain cloud water, and if you're below the freezing level, you introduce quite a bit of cooling from the microphysics scheme, taking that cloud water and evaporating it. If you're above the freezing level and you detrain cloud water, you actually introduce heating because latent heat of freezing before you get rid of it again. So it's a very tricky interaction process. And that's also, yeah, I mean, that's probably the most important here, the interaction between the convection and the microphysics. That's for the current UFS R2O project, the first 2 years, right? Now, if you're talking about the general, about a plan of maybe developing a convective parameterization of the future, then we could probably talk about that for half an hour. Probably be good to make it somewhat flexible so we can switch and exchange various aspects of the convective parameterization fairly easy. Just like, for example, right now it's done with CCPP and physics parameterization as a whole. As I mentioned, a convective parameterization has its own parameterizations inside, right? You have to sort of come up with what do you do with the bubble, with the plume? What do you do with the microphysics? What do you do with this and that? And that's kind of almost like a parameterization and a parameterization. And I think you can structure the code that you can make it so you can swap these things if that becomes necessary. So that's more like the 5 to 10 year line down the road. Or Cliff Maas's idea, we just go in general towards. It's certainly a good parallel approach. And the question is, can you actually ever come up with a way of determining where there will be deep convection? And then can you spawn up a nest in time to treat that? So that would be then the super parameterization approach, or something like irregular grids spawning up.
I don't see any more questions. I guess we can call it a wrap with this last question from Jian then. Thank you, George, for your very informative presentation, and thank you everyone for attending this webinar. Have a good evening and be safe.
Yeah, if there's any other questions, you can always email me and I could try to answer.
Thank you, George. Thank you, everybody.
Thank you. Goodbye.
Bye.
Say bye.